Hi and welcome to the Bare Basics. Today we're looking at transformations of quadratic equations, or if you are in senior, you'll know them as quadratic functions. This little video follows on from an earlier one on transformation of nonlinear functions, and in this case we are using that example to specifically look at the quadratic function. Okay, so let's just quickly recap what a quadratic equation or quadratic function is. So it's nonlinear. That means it doesn't graph to a straight line. The highest degree of the variables in the equation is 2. So that is the basic form of the equation is y equals x squared. As soon as you see an equation that has the highest of any of the powers is a squared, you know that you are dealing with some form of quadratic and you can handle it as such. It has a shape that's known as a parabola. So think Angry Birds when you're actually flinging red and the other birds across. That's generally parabolic motion. Now here's a look at what a quadratic graph or a parabola looks like, and in this case it's a minimum, so it means that the curve is at the bottom of the change in direction is at the bottom of the curve. So its general equation is f of x is equal to x squared. So with this one, I call this the happy curve because it is a minimum, but it's a smiley face. And it's a smiley face because the number in front of the x squared is positive. And that will make more sense in a few minutes when we look at reflecting the equation. And once again, the shape is referred to as a parabola. Okay, so moving along. This was the equation that was introduced in our transforming nonlinear equations video that we can use to transform any equation. Now, when we're dealing with a nonlinear one, it means n cannot be 0 or 1, because if it was 1 or if it was 0, we would have a linear equation. So with our quadratic, n equals 2. So that's the first thing that we can put in there. Instead of n, we can put a 2. And this basic equation will let us alter or transform our equation in many ways. And we're going to break this up by looking at each element of the equation. So first of all, we'll do dilation of quadratic functions. Now that's where we're either going to stretch the function or we're going to squash it down. So if we stretch it, it'll be longer and skinnier, and if we squash it down, it will be shorter and fatter. Okay, so remember, this is our basic equation for transforming quadratics. Now, of these, A is the dilation factor. So it's the one that's going to affect how skinny or how fat the graph is. So what we can do straight away is set h and k to 0, so we only have to worry about the dilation factor. Now, if a is larger than 1, the graph will become longer and skinnier. So here's a graph of a quadratic where a equals 3. Now, have a look at it. It's longer and skinnier, but here's a reminder of what the original graph looked like. So you can see that it's just that little bit, I guess you could say it's that little bit fatter. It still goes through the origin because when x is 0, 3 times x is still going to be 0, so it still goes there. So it actually doesn't move our points on the x-axis, but it does change the points on the y-axis except for 0. Now, if we were to have a as less than 1, it should make our function shorter and fatter. And here's an example. So this one has a as a half, and once again you can see that the equation, it moves out. So think of it as if a is more than 1, it will stretch it this way, but if it's not, if it's less than 1, then it's going to push it down, and as the graph pushes down, it comes out as well. So that is dilation of quadratic equations. Now, A does one other thing as well. It can reflect the quadratic function, and it can reflect it across the x-axis. The way it does this is when the dilation factor is negative A. So if we change the sign, so negative ax squared, the graph is reflected across the x-axis. Now, this is when we go back to what I said before. If A was positive, we have a happy graph, so we have a smiley face. If A is negative, we get what I refer to in class as the frowny face. So this is what the graph looks like when our A value is negative. So it's what we call a maximum graph because the turning point is at the top or the maximum Y value of the graph. Let's move along to the translation or the sliding of quadratic functions. So we can slide our graph to the left or right, up or down. So what we're going to do is we're going to start again with the very basic equation. Now we've dealt with A, so we want A out of the way for this one. So we're going to set A to 1. And we're going to see how H and K can move the graph sideways and up and down respectively. So let's start with K. So we've set A to 1 already. We're going to set H to 0. So our equation is going to be x squared plus K. K changes the value of the y coordinate, so that is, it moves the graph up or down. If it's positive, the graph moves up, because remember, our y-axis is just a number line. So if it's positive, it's going to increase the value of y, so it's going to move it up, and this is what that would look like. So this is our equation of x squared plus 2. So it's simply moved the graph off the origin and moved it up 2. Once again, here's a reminder of what the original looked like, so where it sits going through the origin. And if we were to make K negative, it would move it down. And there is a graph there in yellow that's just a little bit hard to see, but it goes through -4, so it is the graph of x squared minus 4. Once again, let's go back to our original equation, and this time we're going to look at H. So we're going to set A to 1 and K to 0. So H changes the value of the x coordinate. That is, it moves the graph left and right. If it's positive, the graph moves to the right. So here is our equation of x squared minus 4. Of x minus 4 all squared. It's very important, and the way to remember this is that because h is inside the brackets, it is actually changing x before you square it. So this is x minus 4 all squared. So once again, here's our original to remind you what it looks like. And if we have h as negative, so our equation will become x plus h all squared, it will move it to the left. So it's a little bit counterintuitive. If you see in your equation that it has x plus h all squared, think of it as, okay, I've got to go the opposite way to what the sign says. So I'm going to the negative side of the equation, of the number line. Okay, so x plus h, there's a plus sign, so I'm going to actually move it to negative h on the number line, or on our x-axis. Okay, so putting it all together to finish, this is our original equation. If we have an equation that is x minus 2 all squared plus 3, so we have minus 2, so think I've got to go the opposite sign, so I've got to go to plus 2 on the x-axis, and then because my k value is 3, I need to move my graph up 3. So if you've got any questions on this, remember you can ask in class. And that is how we transform quadratic equations. I hope this has made maths a little more bearable for you.